Hi everyone, I'm Tincheng Yu. Today I'm presenting a recent paper on near optimal reinforcement learning with self-play. This is a joint work with Yu Bai and Chi Qin. Let me first briefly introduce our authors. Yu is currently working at Salesforce Research as a research scientist. Chi is currently an assistant professor at Princeton University, and I'm currently a second-year PhD student at MIT. So nowadays, reinforcement learning has achieved a lot of success, and usually the underlying model is Markov decision process, where the agent is interacting with the environment. In every round, the agent take an action, and the environment review the agent, the next state, and the reward. And in that case, the goal is to find the best policy that maximizes the cumulative reward within a fixed environment. However, this definition no longer works in a lot of scenarios. Say in some practical scenarios of interest, like Go, game playing, and poker. In that case, we're actually interacting not only with the environment, but also with the other players, which we call the multi-agent reinforcement learning problem. In that case, the opponents are not fixed, and they can take some adaptive strategies. And this talk is considered a setting of two-player zero-sum game. The problem of the definition of the optimal policy is that in that case, the naive definition no longer works, and we need to consider this more general scenario. One of the most popular approaches for learning a multi-agent RL problem is to learn from self-play. Comparing with learning from playing with human experts, usually self-play is more efficient because we no longer need human domain expert, and as a result, it will cost less for the whole process. In that case, the most important metric for the learning process is efficiency. On the statistical side, we care about the samples efficiency. That is, how many samples do we need to collect before we can train a near optimal strategy. This is important because collecting samples can be expensive. Also, computational efficiency is very important because training deep RL models usually costs a lot of time. Let's say for AlphaGo 0, it is trained on more than 10 to the 7 games and took more than 1 month of time. In this talk, we will discuss how to design brutally efficient self-play RL algorithms in the two-player zero-sum game set. To model the multi-agent reinforcement learning problem, one of the most important model is Markov games, also sometimes known as stochastic games, proposed by Shapley 60 years ago. Here we consider a tabular setting, and I will explain the fundamental concept in this StarCraft example. In the example, one of the most important concept here is the state space. That is, so each state is just the current status for both players, and A and B are the action space for both players. That is the operations you are going to do for the next step. Finally, the horizon H is the length of game. That is equivalent to, say, the number of decisions you are making in one game. So in each game, every time the state is reviewed to both players, and they decide the action they were taking, but without knowledge of what action the opponent will take. And then the reward function is determined as a stochastic function of SA and B, which is then revealed to both players, and then the players transit to the next state S2, and so on and so on. So in that case, so what are the optimal strategies? As we can see, the naive definition of the optimal policies does not work at all because the opponent strategy can be adaptive. To see this, let's consider a slightly simpler problem, that is rock, paper, scissors. In that case, the response is usually how we can best exploit our opponent's current policy. Say that if our opponent always is playing rock, then the best response is the paper. However, if our opponent is changing her strategy, then playing paper all the time may be a very stupid choice. In that case, we need to consider the notion of Nash equilibrium. That is the optimal strategy when always facing best responses. In words, Nash equilibrium is essentially the best thing one can do when in the worst case. So in the rock, paper, scissors example, the Nash equilibrium is just to play rock, paper, scissors in a uniform manner. So our object, since the Nash equilibrium is the best thing one can do from a theoretical point of view, we want to approximate this Nash equilibrium. And the objective here is to find the absolute approximate Nash equilibrium, use a small number of samples with optimal dependency on S, A, and B. One of the most well-known algorithms for learning a Markov game is Nash Q-learning, which is proposed for the two-player setting by the seminal paper of Hu and Wellman in 2003. In this case, the most important quantities to quantify the potential reward in the future is the Q-value function, which is defined for each state action tuple S and B separately. This is the expected cumulative gain of the max player, or equivalently, the loss of the mean player, because we are essentially playing a zero-sum game and starting from a given tuple S, A, and B. And during the whole process, they're doing two things alternatively. The first thing is to estimate the Q value, or this is the way they want to quantify the model. And they perform a stochastic online update to learn the Q values. And once they have a good estimate of Q values, they can go to the second step. That is to compute the Nash equilibrium based on this Q value. This is essentially not harder than solving a matrix game. In our paper, we propose an optimistic version of the Nash Q-learning to further handle the challenge of the exploration, which is a unique challenge for reinforcement learning. There is still one remaining challenge here. So even if one can behave pretty well against a Nash equilibrium policy, it doesn't mean that we already have a pretty good policy, because it could play really bad against the best response. The reason of that is, unlike the fixed environment, in a Markov game setting, the best response for each policy can be different. So even if we're doing well against the Nash equilibrium policy, which is a pretty conservative one, we may be behaving really bad against some other policies. This is a unique challenge in multi-agent RL. To see this, we'll come back to the simple example of rock, paper, and scissors. Here, any strategies will draw with the Nash equilibrium, because the Nash equilibrium strategy is rock, paper, scissors playing in a uniform manner. However, it does not mean that any strategy is a good strategy. Say if you are playing a rock all the time, then the opponent can easily exploit this, and playing paper all the time. But then playing rock all the time is a very bad policy, as you can see. Although it is doing pretty good against the Nash equilibrium strategy. To handle this problem, we developed a new novel algorithm to extract a certified policy from Nash Q-learning, which is guaranteed to perform well against best responses. So here, the extraction process is not straightforward. We still need some further steps to make sure that it is still it is indeed a certified policy. So by the certified policy, we mean that this policy can behave well even under the best response. So now comes to our main result of the paper. If we for the Nash Q-learning, if we run it for SAB over epsilon square epsilon, then extracted policy will be an epsilon approximate Nash equilibrium. Comparing with the lower bound, which is SA plus B over epsilon square, we can see there's still a gap between S times B and between A times B and A plus B. So we also propose a new algorithm called Optimix Nash V-learning, which matches the lower bound with respect to dependence on S, A, and B. We name it as Nash V-learning because we no longer learn the Q value anymore. And we only learn the B value, and we use the follow the regularized leader style algorithm to further improve the sample dependency on A and B. Compared with the existing result, we can see that we are the only we are the first algorithm that could achieve SA plus B sample complexity. So in summary, we developed the first line of near-optimal self-play RL algorithm for two-player Markov games. Welcome to our workshop version to know more about the details about like Nashville learning and certified policies. Thanks.